back to the real number system. In this video, we'll cover section 4.3, where we'll talk about the greatest common divisor and the least common multiple. Let's get started. So our greatest common divisor is the greatest whole number that divides two numbers. Now, neither one of these numbers can be 0. The greatest common divisor is represented by GCD and is also called the greatest common factor, or the GCF. There are several different methods that we can use to find our GCD. The first method is called the intersection of sets method. So here we list all of the divisors of our numbers. Then we're going to pick the greatest number that is in both sets. So here's how this works. Let's suppose we want to use the intersection of sets method to find the GCD. So I'm going to begin by listing the divisors of 20. So I'll start with 1 and 20. Now to me, the easiest way to list these divisors is to count. So I start with 1, 2 goes into 20 10 times. After 2 comes 3. Well, 3 is not a divisor of 20. Then 4 goes into 25 times. And next is 5, and notice 5 is in my list. Now what I've discovered is if I list my divisors in order like this, I tend to not leave out my divisors, and I find them a little bit more quickly. Now let's do the same thing and find the divisors of 32. So 1 goes into 32 times. After 1 comes 2. 2 goes into 32 16 times. 3 is not a divisor of 32. Then we have 4. 4 goes into 32 8 times. After 4 is 5. 5 is not a divisor of 32. 6 is not a divisor of 32. 7 is not a divisor of 32. And notice that 8 is already in my list. So I found all of my divisors of 32. Now, when I'm finding the GCD, I want to look at the common divisors. So 1 is in both list, 2 is in both list, and 4 is in both list. The greatest common divisor is the greatest number that is in both list. So here, our greatest common divisor of 20 and 32, notice our notation, is 4. There is another notation I need to introduce you to that you might see in math labs. Now, I prefer to find my divisors as I've done here. But another notation is D with a subscript of 20. This means the divisors of 20. So in math labs, you're going to see the divisors of 20 listed this way. So D with the subscript of 20 equals, and then you open your braces to represent a set. And then notice we have the divisors of 20 listed, 1, 2, 4, 5, 10, and 20. Now you could do the same thing for the divisors of 32. You'd have a D with a subscript of 32, and you would still find the largest number that's in common in both lists. Either method is fine for a show work problem on a quiz. Let's look at another example. So we want to use the intersection of sets method to find the GCD of 24 and 40. So let's list the factors of 24. First we have 1 and 24, then 2 and 12, 3 and 8, 4 and 6, 5 is not a factor, and then we have 6, and so we have all of our factors or divisors of 24. Let's list the divisors of 40. So we have 1 and 40, 2 and 20, 3 is not a divisor, 4 and 10, 5 and 8, 6 is not a divisor of 40, 7 is not a divisor of 40, and that brings us to 8, which is already in our list. So let's look to see what these lists have in common. Well, they both have a 1, a 2, a 4, and an 8. The GCD means we want the greatest of these, and so our GCD of 24 and 40 is 8. Our next method for finding the greatest common divisor is called the prime factorization method. So here we're going to find the prime factorizations of each of our numbers. Then we'll look for what prime numbers are in common in our prime factorizations. And we want to use the lowest of the powers of each common prime. By the way, numbers such as 4 and 9, these are not prime numbers, but they are what we call relatively prime because their GCD is 1. Let's look at an example. We want to use the prime factorization method to find the GCD of 180 and 168. I can rewrite 180 as 10 times 18. I can rewrite 10 as 2 times 5. I can rewrite 18 as 2 times 9. And then I rewrite 9 as 3 times 3. So my prime factorization is 2 squared times 3 squared times 5. Now remember, our goal with a prime factorization is to have all prime numbers left. So any numbers that were composite, I crossed them out as I rewrote them. Let's find the prime factorization of 168. 168 is 4 times 42. 4 is 2 times 2. And 42 I can rewrite as 6 times 7. 6 I can rewrite as 2 times 3. So my prime factorization for 168 is 2 cubed times 3 times 7. Now when I'm finding my GCD, I want to look for what primes the prime factorizations have in common. Well, notice they both have a 2. And I want to use the smaller power of 2, so I have 2 squared. Both prime factorizations have a 3, and I need to use the smaller power, so that would be 3 to the first power. 2 squared is 4, and 4 times 3 is 12. And so my GCD of 180 and 168 is 12. Let's look at another example. 108 I can rewrite as 9 times 12. 9 I can rewrite as 3 times 3. 12 is 3 times 4. And 4 is 2 times 2. So my prime factorization of 108 is 2 squared times 3 cubed. 72 is 9 times 8. 9 is 3 times 3. 8 is 2 times 4. And 4 is 2 times 2. So my prime factorization of 72 is 2 cubed times 3 squared. Now as I find my GCD, I want to look for what primes these prime factorizations have in common. Well, they both have a 2, and I use the smaller power, so I'd have 2 squared. They also both have a 3, and I use the smaller power, so I have 3 squared. 2 squared is 4, and 3 squared is 9, and so my GCD here, 4 times 9, is 36. Our next method for finding our greatest common divisor is called the Euclidean algorithm. It's based on the following theorem. If we have two whole numbers, a and b, where b is not 0 and a is greater than or equal to b, then our GCD of a and b is the GCD of r and b, where r is the remainder when a is divided by b. Finding the greatest common divisor using the Euclidean algorithm uses this theorem over and over and over until we get a remainder of 0. So here's how this works. Let's look at a flow chart. We start with two numbers, then move to the next box. We're going to divide the larger number by the smaller. Then we're going to look at that remainder. Now, most likely the first time you divide, that remainder is not going to be 0. So we're going to divide again, and we divide the last divisor by the remainder. And we keep doing this until we have a remainder of 0. When we finally get a remainder of 0, that last divisor is our GCD. So let's use the Euclidean algorithm to find the GCD of 10,764 and 2,300. Now my first step is to divide the smaller number into the larger. So I divide 2,300 into 10,764. Well, 2,300 goes into 10,764 4 times. 4 times 2,300 is 9,200, which leaves me with 1,564. Now notice my remainder is not 0. So I take that remainder, 1,564, and I divide it into the divisor, 2,300. It goes one time, leaves me with 736. Again, I do not have a remainder of 0. So I divide 736 into my divisor, 1,564. It goes one time with a remainder of 728. I still don't have a remainder of 0. So I divide 728 into 736. Goes one time with a remainder of 8. I still don't have a remainder of 0. So I divide 8 into 728. 8 goes into 728 91 times. Now notice this time I get a remainder of 0. This tells me that my GCD is that divisor, which is 8 in this case. And so my GCD of 2,300 and 10,764 is 8. Let's look at another example. Again, I want to use the Euclidean algorithm to find the GCD of our two numbers. So I divide the smaller into the larger. So 2,500 into 8,400. 2,500 goes into 8,400 3 times with a remainder of 900. 900 goes into 2,500 twice with a remainder of 700. 700 goes into 900 once with a remainder of 200. 200 goes into 700 3 times with a remainder of 100. And 100 goes into 200 twice with a remainder of 0. So notice I've repeated the process until I got a remainder of 0. That tells me that my GCD is the divisor. So here, my GCD would be 100. So the GCD of 2,500 and 8,400 is 100. We can use GCDs in the real world. So let's look at an example. Two bands that are going to be combined to march in a parade. One band has 24 members and one band has 30 members. We want the bands to have the same number of columns, and so the question asks, what is the greatest number of columns in which they can march? So here, notice I'm finding the greatest common divisor because I'm dividing the bands into columns. For this problem, to me, the intersection of sets method is the easiest. So I'm going to list the factors of 24. Well, 1 and 24, 2 and 12, 3 and 8, 4 and 6. 5 is not a divisor of 24, and that brings me back to 6, which is in my list. List the divisors of 30. 1 and 30, 2 and 15, 3 and 10. 4 is not a divisor. Next is 5. 5 goes into 36 times, and 6 is the next number. It's already in our list. I look at what they have in common. They both have a 1, a 2, a 3, and a 6, and I want the greatest of those. So that tells me here I need 6 columns. Now let's move and talk about what we call the least common multiple. So this is the smallest number that is a multiple of both of our numbers. Again, we have several methods that we can use to find the LCM. So let's look at the number line method. So we draw our number line and then we take jumps on the number line of each number until we land at the same spot. So let's use the number line method to find the LCM of 3 and 4. I'm going to draw my number line and I'm going to count up to say about 15 on my number line. Then I'm going to take a jump of 3 above my number line and a jump of 4 below. Notice that my arrows do not land at the same place. So I'll take another jump of 3 and another jump of 4. Notice I still don't land in the same place. So take another jump of 3, another jump of 4. I'm still not in the same place. But notice when I take another jump of 3, I land in the same place as my jumps of 4. That tells me that 12 is my least common multiple. So here the LCM of 3 and 4 is 12. Notice the notation that we used for LCM. Another way that we can find the LCM that's similar to the number line method is using what are called number rods or Cuisenaire rods, and you may see these in some of your problems with math labs. Rather than taking jumps of 3, you would use rods of 3 or rods of 4 in this problem. until your train, what we call the train, when we put several rods of length 3 together or several rods of length 4 together, that makes a train, until our train is the same length. Next, we have our intersection of sets method. So here we list the multiples of each of our numbers, and we want to find the smallest number that's in both lists. So let's use the intersection of sets method to find the LCM of 8 and 12. So I'm going to list the multiples of both 8 and 12, and I'm going to list, say, the first 5 multiples of both numbers. So 8 times 2 is 16, 8 times 3 is 24, and so on. 12 times 2 is 24, 12 times 3 is 36, and so on. I want to look for a number that's in both sets, or both lists here, and I want the smallest number that's in both lists, which would be 24, and so my LCM of 8 and 12 is 24. Let's look at another example. I want to use the intersection of sets method to find the LCM of 6 and 10. So I'm going to list about the first 5 multiples of 6. 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, and so on. And then I'll list the multiples of 10. Maybe the first 5 multiples. 10 times 1 is 10, 10 times 2 is 20, 10 times 3 is 30, and so on. I want a number that's in both lists, and I want the smallest number that's in both lists, which would be 30. And so the LCM of 6 and 10 is 30. This brings us to our next method, which is our prime factorization method. So first we find our prime factorization. Now this time with the least common multiple, we're going to list every prime that we see. And we want to use the greatest power of each prime. Now when we found the GCD, we listed only the common factors with the smaller powers. But with the LCM, we have each factor with the larger power. So let's use the prime factorization method to find the LCM of 40 and 12. So 40 I can rewrite as 4 times 10, 4 is 2 times 2, and 10 is 2 times 5. The prime factorization of 40 then is 2 to the third times 5. 12 is 4 times 3, 4 is 2 times 2, and so our prime factorization for 12 is 2 squared times 3. When I find the LCM, I don't want to just look at what they have in common. I want to look at every prime factor that's listed, and I want to use the larger power. So I notice we have 2's listed, and I want to use the larger power, so that's going to be 2 to the third. There's also a 5 that's listed in those prime factorizations, and a 3 that's listed in the prime factorizations. 2 cubed is 8. 8 times 5 is 40, times 3 would be 120. And so our LCM of 40 and 12 is 120. Let's look at another example. Again, we're going to use the prime factorization method to find the LCM of 252 and 105. 252 would be 2 times 126. 126 is 2 times 63. 63 is 9 times 7, and 9 is 3 times 3. So the prime factorization for 252 is 2 squared times 3 squared times 7. 105 is 5 times 21. 21 is 7 times 3. And so our prime factorization for 105 is 3 times 5 times 7. When I'm finding my LCM, I want to look at every prime factor. Well, one prime factor is 2, and the only power of 2 here is 2. Another prime factor is 3, and I want to look at the larger power, which would be 3 squared. We also have a 7 and a 5 in those prime factorizations. 2 squared is 4, 3 squared is 9. Bring down the 7 and the 5. 4 times 9 is 36, 7 times 5 is 35, And when you multiply 36 times 35, you get 1,260. So the LCM, the least common multiple of 252 and 105, is 1,260. Our final method for finding the least common multiple is called the GCD-LCM product method, or sometimes you might see it as the Euclidean algorithm, because it does use the Euclidean algorithm in the process. Now we have a formula. You'll notice your formula here. The GCD of two numbers times the LCM of the same two numbers is the product of those two numbers. So what this method does is, first, we use the Euclidean algorithm to find the GCD, and then we use our formula to find the LCM. So you'll have two steps to find your least common multiple here. Let's look at an example. Suppose we want to use our Euclidean algorithm method, or you might see it called the GCD-LCM product method, to find the LCM of 45 and 75. Our first step is going to be to use the Euclidean algorithm to find the GCD. So I divide 45 into 75. 45 divides into 75 one time with 30 left. 30 goes into 45 one time with 15 left. And 15 goes into 32 times with a remainder of 0. Now remember, when I have that remainder of 0, my GCD is my divisor. So here, my GCD is 15. For my second step, I'm going to use our formula. The GCD of two numbers times the LCM of those same two numbers is the product of the two numbers. Our GCD we just found was 15. We're looking for the LCM, so I'm going to let that be X. And it's going to equal the product of our two numbers. So here I multiply 45 times 75. I need to solve for X, so I divide both sides by 15. Now, quite honestly, I don't want to have to multiply 45 times 75 and then divide by 15. So what I'm going to do here is simplify this fraction. 15 goes into itself one time and into 45 three times. So now I just need to multiply 3 times 75, which is 225. So our LCM of 45 and 75 is 225. Let's look at another example. Again, we want to use the GCD-LCM product method, Euclidean algorithm, to find our least common multiple. So I begin by dividing the smaller number into the larger number. 126 goes into 303 two times with 51 left over. 51 goes into 126 twice with 24 left over. 24 goes into 51 twice with 3 left over. 3 goes into 24 8 times with a remainder of 0. When I have the remainder of 0, that tells me that my divisor, 3 in this case, is my GCD. Now I'm ready to use my formula. That's my second step. So the GCD of two numbers times the LCM of those two numbers is the product of those two numbers. Our GCD is 3. I'm trying to find the LCM, so I'm going to let that be X. And then I multiply my two numbers together. So here I'd say 126 times 303. To solve for X, divide both sides by 3. Now again, I really don't want to multiply 106 times 303 and then divide by 3. So I'm going to simplify. 3 goes into itself one time and into 303 101 times. So I have 126 times 101, which is 12,726. So here, my LCM of 126 and 303 is 12,726. Let's look at a real-world problem with our LCM. So hot dogs are sold 10 to a package, while hot dog buns are usually sold 8 to a package. So what's the least number of packages I have to buy of each so that I have the same number of hot dogs and hot dogs buns? This is a least common multiple problem because notice here it says the least number of packages, and I'm buying several packages, so I'm looking at these multiples of 10 and these multiples of 8. Again, to me, the easiest method to find the LCM here is to use the intersection of sets. So I'm going to list the multiples of 8 and of 10. I'll list, say, the first 5 multiples of 8. 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24, and so on. And I'll do the same thing for the first 5 multiples of 10. 10 times 1 is 10, 10 times 2 is 20, 10 times 3 is 30, and so on. I want the least number that's in both lists. That would be 40. So 40 is my least common multiple here. Now the problem doesn't ask me how many hot dogs and how many buns. That's what this 40 represents. I'd have 40 hot dogs, 40 buns. The problem asks me how many packages. Well, to get 40 hot dogs, 40 divided by 10 hot dogs gives me 4 packages of hot dogs. And since there are 8 buns to a package, 40 divided by 8 tells me I would have 5 packages of buns.